Hello everyone. In this class I actually wanted to talk about NAND and NOR gate implementations, but maybe I'll have to give you a slight brush up of what gates actually are in Boolean algebra. So when you think of an operation, say it is an addition or a multiplication or any operation, any algebraic operation, you can have an equivalent representation in Boolean algebra, and that is obtained through gates. So first of all, let us look out what these logic gates are. Logic gates are of many types. The basic ones which you have probably already seen are AND, OR, NAND, NOR, so inversion. These are the basic things. So just let me just brush up for 1 minute. This is the first sort of gate. It is a simple arrow and a line extension. This is a buffer. If you are giving A as input, you will get A as output. If you are giving 0 input, you are getting 0 as output. If you are giving 1 as input, you are getting 1 as output. This is the first sort of gate. This is buffer gate. So the next gate you are going to look at is inverter gate. If you are giving A as an input, you are going to get A complement as an output. That is, if you are giving 0 as input, you will get 1 as output. If you are giving 1 as input, you will get 0 as output. This gate is inverter. That is a buffer. Buffer gives you same value, inverter gives you opposite value. Right? These are the basic gates, two basic gates. The next gates, these are not important also for your exams. The next gate you are going to look at is the OR gate. The OR gate has 2 or more inputs and 1 single output. For simplicity's sake, I'll take 2 inputs. I'll take A and B as inputs, and what shall be the output? We'll take Y. We'll take Y is the output. So the property of the OR gate is we have 2 inputs. Zeros and ones are also considered as low and high or off and on. 0 is considered low, 1 is considered high. In other cases, 0 is considered off, 1 is considered on. So zeros and ones have many meanings in different applications. For example, you are taking a motor, 0 can be off and 1 can be on. If you are taking some dimming or brightening of light, various things. 0 is low, 1 is high, 0 is off, 1 is on. So this thing has just one rule. If any of the inputs is on, let me take 1 as on and 0 as off. Remember this point. 1 is on, 0 is off. If any of the 2 inputs is on, then the output will be on. So the possible combinations are both the inputs are off. This is A and this is B. A input is off and B input is on. A input is on and B input is off. Both the inputs are on. So according to the condition, if any one input is on, output is on. On. Only in the first case, the output will be off. This is called OR gate. OR gate. So the algebraic expression which is denoted by OR gate is, you can guess, it's A plus B. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1. So this is nothing but A plus B. This is the OR gate. If you are adding a bubble at the end, it becomes NOR gate, which is nothing but not OR. So OR gate and NOR gate are just opposites. So whatever you are writing here, it becomes the right opposite. You have 1, 0, 0, 0. Opposite of OR is NOR gate. The next sort of gate we look at is the AND gate. The AND gate is pretty important, and that AND gate, it depicts multiplication, product. AND gate looks something like this. This is the AND gate. So in this also I'll take just two inputs for simplicity's sake, and the output I'll call it as Y. According to AND gate, the output will be on only if both the inputs are on. So the output will be on only if both the inputs are on, which is I can take A, B and Y. A is of, B is of, A is of, B is on, B is on, A is of, both are on. So the only case in which the output will be on is this. In the rest cases, the output will be off. This is AND gate, and this gate shows product, that is A into B. Right? Just look at it yourselves. A 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. So this is nothing but a summation gate. This is AND gate. And by the way, I just forgot to tell you, OR gate is A or B, this V shape. And NOR, which is not OR, is represented by this complement. AND gate is represented by A, this reverse V, B. And NOR is NAND. NAND will be this. AND is without the complement, NAND is with the complement, which is not AND. Or NOR, which is not OR. And NAND, which is not AND. So finally, NAND gate we'll just look at, just this bubble, and will be the opposite of AND, 1, 1, 1, 0. Output is off only if both the inputs are on. That is about NAND gate. AND, NAND or NOR. Hope you are clear with all this. We saw inverter, which is also NOT gate, you can call it as. And you saw buffer, you saw AND, NAND, OR and NOR. And XOR, XNOR are two gates. I'll just tell you briefly about it. XOR gate I have taken two inputs. This is XOR gate. In XOR gate, the truth table is something like this. Tell me the various combinations. 0, 0, 0, 1, 1, 0, 1, 1. A is off, on, off, on. The output is when at least only one input is on, then it will be on. If both are on or both are off, output will be off. This is the property of XOR gate. XOR gate is represented by this operation A plus, and you put a circle around the plus and write B. This XOR gate is used in half adder circuits. I'll tell you what half adder circuits and binary codes, I'll tell you all that later. For the time being, it's used in half-adder circuits, and this is the XOR operation, and this is the XOR truth table. XOR denoted by that, right? XNOR, which is XNOR, you are adding that M, which is not of XNOR. Simply you are just adding a bubble there. So this Y values, this will become 1, 0, 0, 1. This will become the opposite. So for XNOR, this is the representation. You will put a complement above that. Right. Now that if you have any doubts regarding gates, just ask. If you are clear with it, we'll just go to NAND and NOR universal implementations.